to you.
Thank you, Halleluya. Today is our great honor to have Gayle Febbo giving a talk on a very exciting subject, again related to porphyries. Gayle got her bachelor in 2007 in geology, and then she continued her master's in structural geology at Mineral Deposit Research Unit, University of British Columbia, 2016. Then she started working in mineral exploration. She has over 17 years of work, including geological mapping, petrographic studies, structurally controlled and deformed gold systems in British Columbia, including KSM and Galore Creek. She's currently Vice President Exploration for Kingfisher Metal Corp, and early stage explorer of high-grade copper and gold systems in British Columbia. Gayle, stage is for you. Take it away.
Thanks so much, and thanks for having me. Before we dive in, I'd like to acknowledge my co-authors. We have a great collaboration here among industry, academia, and government, the BC survey. So I'm presenting on 2 districts, but a lot of other insights have gone into this from other map areas. Gold systems in Stikenia are subject to pre and post porphyry deformation, and unraveling these structural histories can be time consuming and complicated. And so what I'm presenting on today are some of the patterns that I see in the field at deposit scale and regional scale. And I think these are important to exploration and pretty useful for anyone working in this neck of the woods. We're going to talk about a lot of different structural features, porphyry features, deformation features, and a lot of different geometries. And so just as a guide for this talk, I want to give you our hypothesis right up front so you can follow a little better. So the idea here is that north and east trending structural patterns that we see in this area reflect a left propagating Paleozoic rift, and that northeast trending structural patterns reflect Mesozoic rifts, more specifically late Triassic, or at least active by that time. Okay, so let's dive in. For those of you who aren't familiar with BC, we really have 2 porphyry camps here. So there are the porphyries that formed offboard of North America, and those that formed in place on the margin of North America. And those that formed offboard are part of either Stikenia, the deeper green, or Quinalia, the pale green. And what really matters here is that the gold-rich systems are almost exclusively part of the island arc setting. And you can see these are porphyry occurrences here. So the yellow dots are the gold porphyries, and you can see they're really popping up where you're either in Quinalia or Stikenia. The copper and gold porphyries you can find throughout, and Mali is restricted to a continental setting. So the 2 we're talking about, we have Galore Creek and KSM. Galore Creek, silica undersaturated alkalic porphyry cluster, KSM high K calc-alkalic porphyry cluster. Right now, KSM is sitting at 76 million ounces gold and 17 billion pounds copper. So it's actually the largest resource of gold in the world. So pretty significant system there. And Galore Creek is really important because it's a high relative grade for porphyries. Okay, we're going to zoom in to a little bit closer. So this is the Northwest Stikenia area I'm talking about. This kind of triangular green is Stikenia. So up here, Galore Creek, most of the strain that we see in the rock predates porphyry emplacement. Down here at KSM, most of the strain that we see post-dates porphyry emplacement. And so it's kind of neat. We have 2 different porphyry systems, right? More alkalic, calc-alkalic. And then we also get 2 different relative timings for flattening in those districts. So it's a nice, these two make a really nice comparison. And now we're going to just zoom in to the regional setting here at KSM. Okay, so are the KSM deposits, Kerr sulfurettes, Mitchell iron cap, and then of course Brucejack just here to the southeast. SK Creek and Treaty are also in this neck of the woods. So first I will point out the most prominent regional structural features that we see in the area of KSM. And those are the Forest Kerr and the South Unic Harrymill. And these are pretty significant corridors of structural influence. The Iskut River lineament was proposed by Danny Aldrich. And this is a pretty major lith break, as you can see on the map here. And so these really bound this whole district. And so they're pretty important features. In addition to this north and easterly features, we get a northeasterly trend as well. So the Newmont Lake Graben, Triassic age, as well as the SK Rift here, northeast. And we're just going to zoom in to the KSM district here. So some of the structural patterns that we see, well, for one, these features are the faults that we see in this area are fairly complicated, let's say. So what is really common to observe are multiple kinematics along strike. So for example, normal, strike slip, reverse faults, all within one structural trend. The sulfurettes thrust is a really good example of that. And it's a regionally mapped, complicated structure. We have strike slip segments, reverse and thrust geometry, as well as north and northeast strikes. And we see both broad ductile domains as well as focused brittle domains within that. And really I'm pointing to fault reactivation. In addition to that, what's really common in this area are a coincidence of faults and folds. So here in SK, we have a normal fault trends parallel to the fold trends in yellow. So the normal faults are red. Treaty fault parallels the fold trend here. That's also parallel to this thrust trend. Kerr fold trends paralleling the sulfurettes trend. So this is really common to see through this area. And I'll highlight here as well the Jack Formation, this gray. So this unit is important because it was deposited just prior to porphyry formation. So this is giving us a bit of a clue as to what was going on at that time. And I'll just point out here that you can see it's quite abundant in the KSM area compared to other areas around here. And so we had something unique going on in that area. And you can see that it is structurally controlled basin. And so it's fault bounded. The geology of KSM is pretty fascinating. There's a lot of really good papers out there. I won't get into it in this talk, but I'll just direct you to the new CIM papers, as well as Michelle Campbell's PhD, lots of good stuff coming out. But what I do want to highlight here is that it's really has a long lifespan. So we have, starting with Kerr, and this is a pretty crude representation of her geochron work, but Kerr is the oldest, around 202, iron cap sulfurettes 94, 95, and then Mitchell Snowfield 91, and then Brucejack follows at 186 to 183. And so we're talking about 20 million years of gold rich systems. So, why do you have so many great deposits focused in such a small area over that time? I think probably there are a lot of components to that answer, but I'm looking at the structural angle, and I think that there's an important structural common denominator. So we're going to start working backwards in time arbitrarily. So we're going to start with Mitchell Snowfield, and then we'll have a look at iron cap and then Kerr, and just look at some of the structural patterns that we're seeing there. So the Mitchell deposit, this is where it all started. This was my master's thesis, and I was pretty fortunate to have Joanne Nelson mapping in that neck of the woods at the time. So one of the first things that we noticed working on this deposit is this incredible outcrop. It's the sheeted quartz vein zone right here. And it strikes east-west. It's one of the most incredible outcrops I've ever seen. It's several hundred meters in strike length, a couple hundred meters thick, and it's 60 to 90% by volume quartz veins. And what's really struck me is that the KSM district is a northerly linear of porphyry centers, but the overwhelming geometry in the deposit itself is easterly. And so you can see here an easterly trend to the quartz vein abundance contours. And then these are stereonets of the porphyry veins. And there is a scatter, which is normal because you have stockwork. But overall, easterly is the geometry that we see there. So the Mitchell deposit was overprinted by Skeena fold and thrust belt flattening. So we have two phases. What we see is a pretty marked pressure solution cleavage. This is what it looks like in thin section. And again, easterly. So it overprints the porphyry veins, as you can see here. The cleavage is axial planar to these vein folds. And then there is a less intense flattening event that follows that with north plunging folds. And so overall, the deposit area, this easterly fabric is essentially intensified by this deformation overprint. So you have a pre-existing porphyry fabric, and then now we've added the Cretaceous layer to that. This slide was generated from Mitchell, but it really could have been made at Kerr or at Brucejack because you see this everywhere. And that is that flattening, the degree of flattening is a reflection of the content of phyllosilicates in the rock. In other words, the amount of alteration or the phyllosilicate alteration, I should say. And so where we get phyllosilicate rich alterations, we can have 20 to 50%, even higher flattening estimates. And then we can have other rocks that, like potassic altered rocks, that really don't see that. Now we're going to move to iron cap. So this is a plan view of iron cap, and this is from Michelle's CIM paper. So you can see at iron cap something very different is going on. So here we have the quartz vein abundance in plan, and these are counted in drill core. And we have northeasterly alteration patterns, similarly northeast, plutonic geometry, gold, copper, and moly all agree as well. So a pretty strong fabric, different from Mitchell. And if we look at Kerr, well, I'll first point out, so here was iron cap, this northeasterly pattern. And now we're going to jump down to Kerr. Kerr has a pretty elongate geometry all around, so a pretty high aspect ratio. And it's overall a northerly trend. So this is the copper. And then in cross section, you can see this as well. These black patterns, these are the quartz vein abundance contours. And so this is echoed by that, as well as copper. I could have put other maps or sections on here, but you can see this is reflected also in the plutonic geometry and the alteration geometry, which are both very high aspect ratio. So Kerr is also overprinted by Skeena fold and thrust deformation. The flattening fabric that we see at Kerr is north to northwesterly in geometry. And you can see here, it clearly overprints the veins, so it's late. And that foliation is roughly subparallel to the porphyry patterns that we see. This photo is maybe a little misleading because I've captured kind of a rare vein that cuts across the foliation. But what's more typical is that the sheeted veins are parallel to the foliation that we see there. So to sum up what we saw at KSM, the geometric patterns of the porphyry, which span about 202 to 191, are subparallel within a given deposit. However, the deposit geometry is different. So at Kerr, we have this northwesterly Mitchell and Snowfield, easterly, and Iron Cap, northeasterly. And I'll just highlight in this slide that these geometries are reflected in the regional patterns we see as well. The South Unit Caramel, Iskit, and then the Treaty Fault and Fold trend. And I think that is important. Okay, so we're gonna just locate ourselves here again. So we've been talking about KSM, and now we're gonna move up to the northwest to Galore Creek. Again, similar to KSM, a really incredible geology story. Unfortunately, I won't have the time to really introduce this properly, but there is a lot more good reading you can do on Galore. So just to quickly introduce, this is silica undersaturated. So we get void syenite intrusions, for example, that are associated with these mineral systems. And I'll just introduce on this slide, this faunolite unit. And so what that is it's the volcanic equivalent of the Galore intrusions. And so these kind of lime green units, this is volcanic activity that just preceded porphyry emplacement. And the porphyry intrusions, the first phase, are pretty well centered in that. So it's intruding its own volcanic pile. And this unit would be comparable to the Jack Formation, basically. Okay, normal faults at Galore Creek are pre-porphyry in timing. We have north strike, northeast strike, east strike, and many are healed by hydrothermal plutonic activity related to porphyry emplacement. And so where you identify the normal fault, if you walk it out, you can find areas that the porphyry is overprinting. They have a spatial association with fold corridors in outcrop. This is the most interesting part of this story, at least structurally. The Butte High Strain Zone, it's up to 1 kilometer wide. It's a foliated corridor, and it includes a lot of different structural things, but it's really a corridor of relatively much more flattening. And so you can identify isoclinal folds, a lot of different things in here. And then when you go outside of it, you're really not seeing that so much. And what's really interesting is that this is cut by Galore intrusions. And so it overprints the volcanic pile that preceded porphyry emplacement, but it's cut by the Galore intrusions. And so that indicates that flattening at Galore preceded porphyry emplacement, but it also overlapped broadly with that alkaline magmatism. And this is what it looks like in the field. So here's a lucite ferric volcanic unit, and it's overprinted by this flattening. And then this material is cut by Galore intrusions. And so that flattening overlaps with alkaline magmatism. And here's another similar example. So this is a basalt layer, but it's actually got faunolite above and below it. So, you know, it's part of that volcanic package that just predated porphyry emplacement. And here's a fold that's cut by planar sulfide veins. And there are actually quite a few examples of that. So it's an important timing constraint that sets us up here. If we look at the porphyry patterns at Galore Creek, they are quite changeable. And so what you see is in the field is there's a lith change. And so here we have a lithology boundary. But instead of finding a fault fabric or a deformation zone, what you find are outcrops like this, banded pyrite K feldspar hydrothermal material. And you'll see sheeted veins, subparallel porphyry intrusions, and where that lithology boundary is, where you would interpret a fault, the deformation zone isn't there. And so what I interpret for these is that these are healed paleo faults. And what you find in the field is that the porphyry patterns coincide with these lithology breaks. And these breaks also are parallel to fold trends. And in fact, the fold trends, the folds really pick up as you get closer to that lith break. So you'll see a higher amplitude and a shorter wavelength of folds as you approach it. Post-porphyry deformation, we get the saddle thrust, east-northeast striking, and the Copper Canyon thrust following the saddle thrust. And, you know, these are both sub-parallel with normal fault segments in their footwall. And again, just hinting at fault reactivation. So there's really no faults you can map in either of these districts that you would consider very simple. It's very common to find these kind of complicated kinematic features along these deformation zones. So the summary for Galore Creek, the flattening that we see there, which I've bracketed around 212 to 208, it precedes porphyry emplacement, but overlaps with the volcanic equivalent. Fold trends parallel pre-existing fault trends, and the porphyry patterns that we see, and by porphyry patterns, I mean, you know, alteration, porphyry intrusions, metal zonation, sheeted veins, they parallel those fold and fault trends in the field. Okay, so we've looked at a lot of stuff. Let's kind of boil this down. This slide kind of captures what I would interpret is the reason for this. Maybe there's more at play here, but this is my first kick at the can. So in both cases, we start with some kind of basin architecture. Deformation happens at different times, right? So at Galore Creek prior to porphyry and at KSM post. So as we go from the basin setting at Galore Creek to deformation, we would invert the basin, generate folds that parallel the basin faults. And we could have normal and reverse faults in the same area. And so that would explain the complicated faults. This would also explain the parallelism of folds and faults. And then following that, we would have porphyry emplacement that heals those pre-existing fault fold corridors. And then we see the sheeted veins paralleling that. So that would be kind of the timeline there. That at KSM, we start with the basin architecture. So here, this would be faunolite in these areas. And here we have the Jack Formation, followed by porphyry emplacement. So sheeted veins, intrusions, elongate alteration, they're following what was pre-existing. And then following that, we have deformation, and flattening in that case is focused where the porphyries are. And that's because we have phyllosilicate rich alteration types. And so we get more flattening. So we get basically an increase in deformation fabric in these corridors. And we didn't really talk about the folds very much, but we have the folds within the phyllosilicate rich areas, but there are regional folds that parallel these as well. And so in both cases, the result would be a parallelism of sheeted veins, alteration, deformation fabrics, fold trends, both normal and reverse faults. So that's the deposit scale thoughts that come from those patterns. As far as the regional, these are kind of some of the significant regional structural corridors that I've seen in those districts. So if you plot these at this scale, this is kind of what it looks like. And now if you want to start speculating, this is what I would probably draw. So in this view, we have the northerly corridors define a sort of left migrating pattern. I think what's most conspicuous about this pattern is that the northerly corridors have a relatively consistent length, around 40 to 60 kilometers. So it's pretty distinct. The easterly corridors have longer strike lengths, some more than 100 kilometers, and they are associated with inflections in the Bowser Basin. So you can see kind of changes along these easterlies, especially the Iskut River, for those. And just to note, these lineament interpretations are weighted on higher density of mineral occurrences. So it's an attempt to filter out strictly younger faults. So something that formed and just purely cross cuts, the hope is that it will take that layer off. And if we do the same for the northeasterly corridors, what we see are that these are more planar in their trace, and they appear to have a narrower width of influence and less lithological offset. I should have pointed out, so some of the criteria I used for these are looking at some of the topographic lows. So some of these aren't associated with mapped faults. You know, you can see like marked topographic lows and subparallel, you know, lithological and structural boundaries, or several structural features that are parallel. So this is the interpretation for the northeasterly. So if we turn back on the mineral occurrences, I think that things really start picking up where you're seeing interference between easterly, northerly, and northeasterly. So, you know, maybe having 2 or even 3 of those present. In the case of the Stewart district, there appear to be 2 good northeasterly features there, plus this orthogonal component. So, you know, maybe this is hinting at something important happening there. So, you know, what are these northeasterly corridors? We have some clues from KSM and Galore, but it's difficult to study those when everything's altered. So let's take a look at the tabletop fault. It's a dextral strikeslip fault with evidence for southeast side down displacement in the latest Triassic. And Emily Miller and her team did a really good job of this. And this is more of the kind of work we need to properly characterize these structures. You know, a lot of what I'm presenting is kind of speculating on what they might be, but this really pins it down quite nicely. So I'll first point out, this does a really good job at demonstrating the complexity of these corridors. So we have several subparallel northeasterly faults. Whoops. Strike slip, reverse, and they're paralleled by fold trends. So what Emily demonstrated is that the Kinsketch conglomerates were deposited here to the southeast based on a major stratigraphic difference. And I'll just point out the cross section. It nicely shows how basin inversion could have caused this parallelism. So you get a pop-up structure because this would have been lower, and fold trends paralleling the faults. But this northeasterly corridor is several kilometers thick in its expression of this northeasterly structural fabric. And this is the big bulk target over here. So that's a pretty important clue. And she's constrained this to latest Triassic. So this is indicating that this geometry was present prior to porphyry emplacement, at least in the case of big bulk. So the northerly and easterly corridors, pretty tricky. These are pretty cryptic, but I will point out, if you plot the Paleozoic magmatic axes, you see northerly and easterly trends. This is a bit of a function of erosional level, so it's a bit tricky, but it may indicate that geometry was present as far back as the Paleozoic. So to me, looking at this pattern, it does resemble a rift pattern with a series of easterly transform faults. And here's a modern analog with this one is moving the other direction. But this is a possible reflection of Stikinia's basement architecture. So if there was a rift present in the Paleozoic, that would have been translithospheric by definition. And that would have provided the pathways for magma ascent over numerous metallogenic epochs. And many of these districts don't just have one age of mineralization, they have numerous. And that could be the common denominator. And, you know, this geometry does sort of capture a triangle. I don't know if that's true or not, but, you know, what is the cause of this, in my opinion, may not actually be that important. I think recognizing the patterns is really important, and I think that really does work. Probably pinning down what it is not going to be that easy. It's certainly not easy to prove. But what I'm really interested in is just the exploration implications. And I think looking at these patterns has implications for the deposit scale and the regional scale. You know, the most important takeaway is that the structural setting at KSM and Galore Creek is certainly not unique. You can see these patterns throughout the region. You know, this is a reproducible geometric pattern. So, you know, if you focus exploration on some of these gold-rich structural features, I think it has the potential to reduce your search area and reduce costs. Yeah, thanks so much for having me. And as I mentioned at the beginning, this is just 2 study areas that I'm presenting on, but there's a lot of conversation, a lot of other projects in the region that have come into play for these ideas. And I'd like to thank everyone. I'd love to incorporate other people's projects. So if anyone wants to share what they're seeing, please reach out.
Okay, thank you, Gayle. That was pretty awesome. So for the discussion part, I'm going to ask John Nelson to join us and starting this session.
There, okay, now you can hear me. So I just want to thank you so much, Gayle, for this great talk, and to tell the other participants that I've been watching the development of Gayle's career and her ideas over the last 8 years, and starting from puzzling over the Mitchell deposit, which is really complicated, her interpretations have grown in sophistication to the point that you see this wonderful presentation today. So my personal interest is in tectonics. So I want to start, you guys can go back to mineral exploration after this, but I just want to start with the hardest question, which is, okay, it's convincing to us that this is a pattern of Paleozoic rifts and transforms, but where are you going to find the smoking gun to prove that? And I just wanted to drop a little hint that there are Paleozoic seabed massive sulfide deposits, volcanogenic massive sulfides of Paleozoic age in Stikenia. So have you thought about looking at those, like Tulsa Chief and more?
Yeah, I've been asking myself the same question, Joanne. You know, how do you make direct observations that could demonstrate this? I don't know. Yeah, looking at the mineral systems at that time, you know, one idea I had was if we mapped the expression of these structural features in Paleozoic rocks, in Stahini and in Hazelton, because these would be vertically propagating over time. So if they initiated as, you know, in Stikinia's basement, with every subsequent layer, they'll propagate upward and express differently. And I think in some areas, they can be draped and almost masked completely. And so there's sort of this cryptic, clues that they are present, but it would be easy for someone to say, well, that doesn't exist there because you can't map a fault there really. But in some areas, the stratigraphy can drape over, but it would be neat to see, to compare its expression in the different layers over time and see, you know, how does that change? And is that a reproducible pattern? How does that change in thickness? Yeah, I'm not sure.
That's a really good answer. The portrait of a long-lived fault. Okay, thank you.
Okay, thank you, John. I have a question for you as well related to these faulting systems. Are these ones the deep crustal faulting systems?
Sorry, can you say that again?
Are these faults deep crustal faulting systems?
Well, what I'm proposing is that they would have initiated in Stikinia's basement, and so they would have been translithospheric at that time. So they would have gone through the lithosphere, and then subsequently several layers would have been placed on top of that or deposited on top. And with each layer, that fault would propagate upward. So at every stage, that would be a deep crustal structure.
Okay.
Does that answer?
Yes, got
Okay.
it, got it. Thank you. Aaron, do you have a question? Would you like to unmute yourself and ask your question?
Sure. Thanks. Yeah. Thanks, Gayle, for the great talk. That was really impressive, and for somebody like me who's still like learning about this golden triangle and what it has to offer, is really interesting. I think recently a company actually announced, Enduro Metals actually announced the discovery of a new porphyry deposit just north of that this Bronson airstrip.
Yeah, Burgundy.
Yeah, so there's this Burgundy Ridge. It's an alkalic copper gold porphyry, and it's sitting along one of these northeast fault systems, the McClimate fault or something like this.
Exactly.
But it's not near where you mapped your east-west, north-south rift controls, which all of the others.
Yeah, it is. So if I'm not mistaken, aren't we? I think we're right in here.
Yeah, so it's like, but it's sort of more away from them than the others.
It's a mirror image of KSM. So we have the east. One thing I want to learn more about moving forward is, what is the width of influence of these? And I almost think you could draw an axis that's okay. Here's the core area of influence, and then you have a moderate area of influence and a distal. And so to me, KSM is sitting in that kind of distal most influence of each of those easterly and northerly structures. So this is a Triassic graben. So we have the exact same setting as Galore Creek. We have a northeasterly structural feature going through there, and we're sitting in the distal influence, potentially the distal influence of the forest Kerr and the isket. So it's identical, and it's a really important discovery. It's there are Galore Creek suite intrusions throughout the Golden Triangle, but there aren't very many discoveries of true alkalic deposits like that. So it's of pretty big interest.
Yeah, and we're along these lines for the new one. At least some of the pictures that I've seen from their like news reports, it doesn't look deformed. It looks more like the Galore Creek, if I paid attention right. It looks like it's post deformation.
Yeah, well, one thing I would mention is that because the alkalic systems have a high K-feldspar content in their alteration and the intrusions, they're very competent. And so at Galore, it actually took quite a lot of work to demonstrate the timing of deformation, because the intrusions and the alteration system, they're so hard, they're not taking on that fabric. So at KSM, it's really easy to see that they've been overprinted because it takes on the fabric much more compared to the rock around it. So I wouldn't say not seeing the fabric would rule out that it's been overprinted. I mean, being so close to all this, fold and thrust belt deformation, I would expect that Burgundy would be overprinted by potentially pre and post porphyry. So it's probably even more complicated than Galore.
But this is cool because along this linear trend, it kind of is filling in one of the gaps there. So where's the next gap to fill?
In terms of exploration?
Yeah.
Well, that's a secret.
Good. Okay.
I mean, I think just in general, it's using these patterns to explore under ice and cover. It's really hard to explore this area. It's very steep, very technical in terms of just mountain skills. Lots of glaciers, lots of till. It's really not easy to explore. And I think the obvious thing is to look at these areas that are more prospective, in my opinion, and just do standard exploration, ground surveys, soil surveys, explore undercover and under ice, focused on these corridors. So I think people have looked everywhere here where there's outcrop and you can fly a helicopter easily, but maybe focusing a little more time where you don't have outcrop.
Cool. Yeah, thanks so much. It was great talk, and I'll mute now.
Thanks, Gayle. It looks like we don't have so many questions today, but we have one last question, and it is taking us on the exploration route. Malanga would like to know if there is any potential or proven mineralization that can be linked to the number of veins or the textures within the two regions we have just discussed.
Is there a relationship between mineralization and veins?
Yes, or the textures that you've just spoken about.
Yeah, that's actually a really good question. So at KSM, one of the, sorry, I'm gonna make you dizzy here. In drill core, we count the quartz vein abundance. And so over a 2-meter interval, you actually measure how many quartz veins there are. So, you know, you're gonna say there's 20 centimeters of quartz veins over the 2 meters. And so you can see how remarkable it is actually the abundance here, right? So at Mitchell, this really high abundance, like this is a lot of quartz veins. And they have that data for all the deposits. It's really neat. And at Mitchell, at least, I can't speak as much to the other systems, but there was basically a 1-to-1 correlation with quartz vein abundance and gold mineralization. And that's the only reason we spent all that time to count them. And from what I've seen, that's not unique to porphyries. You know, it can be a pretty powerful tool for other systems as well. And it's a great thing to map in the field as well. It's not something you see a lot, but it's pretty easy to do. You know, you just literally count or measure in the field, and then you can make maps like this. And they're really a heat map, right? It's a map for the flow pathways and, you know, how much fluid was going through there. And it's a really, really good exploration tool.
Thanks, Gayle. I like that you just said it's easy, just go out there, count these veins and just map them out. There's another question from Erin. Erin, I'm going to ask you to unmute and ask a question, please.
Okay. So looking at the geometry of the golden triangle, you have like this roughly northeast striking boundary on the top, on the northern part, or the northern, you know, the northern edge of the triangle. Why?
Sorry, what are you referring to?
So this, like, yeah, so this between Galore Creek and Red Chris, you have like but the golden triangle doesn't particularly, like, it's not thought to like extend to the north, but why?
All depends on what slides you look at.
Okay.
Yeah, can I invoke Joanne for this one? I think it's much more of a tectonic question.
Am I unmuted?
Yes.
Okay. So Erin, yeah, good question. Gayle and I draw the golden triangle differently. She's a mineral explorationist. Mm-hmm. So she flips it right against the known deposits. So she runs the northern part between Galore and Red Chris to Toga, but I would draw it east-west along that lineament that goes right north of the Red Chris to Toga district. And we have this thing we call the Galore Belt, which is, you saw the northerly structures at Galore itself. There's this whole northerly belt that extends from that top east-west linear, which is roughly along the Stikine River. It goes all the way south to the lower Iskut River in the Snip-Bronson district. And there are a bunch of little alkalic intrusions along there. So the mineral potential does not end at Galore Creek. You can push it farther north. The true limit is the northern side of where you get the Hazelton group and its associated intrusions. Farther north, you're up into an area called the Stikine Arch that at the end of the Triassic goes quiet and is just uplifting, but there's not magma supply to create mineral deposits there.
Okay, no, that's a good answer.
Mm-hmm.
Yeah, no, that's exactly kind of It's
Yeah,
good to differentiate between the mineralization, the mineral explorers and the tectonic,
the
actual tectonic domain.
tectonicist. Oh, and there's yet a third definition of the Golden Triangle that just cracks me up. Our colleague Bram Van Straten admits that it's kind of arbitrary. And he says, no matter what, the proponent's project area will be within the Golden Triangle that they present.
Yeah.
That's fair.
I really like the golden horseshoe too. I think that one actually is pretty geologically real.
There's another question here from Malango. Malango, would you like to unmute and ask your question, please? All right, So Malango says, I see in some slide pyrite with K feldspar. Is there any potassic alteration in your shear zone?
We're talking about Galore Creek.
I'm guessing anything where you have your pyrite associated with K feldspar. Malango doesn't really specify which area this question belongs to.
Yeah, that sounds like, I think you're probably talking about this slide.
Yeah.
At Galore Creek, the alteration assemblage, when normally I characterize porphyry alteration in terms of a core assemblage, proximal, and a distal assemblage. And I think for some people, they might think of potassic, phyllic, propylitic. But I like to build that assemblage based on what you see in the field and weighting it on sulfide assemblage. And one thing that's really neat about Galore is there's K feldspar in every assemblage. So you get it in a core, proximal, distal, high level, epithermal, absolutely everywhere. And so alteration and sulfide veins cut the high strain zone. On the map scale here, but in several other examples and up here. So there's K feldspar because the unit that it places into is a faunolite. So there's quite a lot of that. And then you overprint it by porphyry alteration. So yes, but it's post-flattening. And so the sulfide veins and the K feldspar alteration cut the foliation and basically wipe it out where you see it overprinting. Does that answer the question?
Yeah, it looks.
Yes, that's what I think. Thanks for the clarity. I would like to ask Jeffrey to please unmute and ask the question. Jeffrey?
Gayle, Jeff Hedenquist here.
Hi.
Hi, not specifically about KSM, although including KSM, anywhere you first start mapping, if you don't know what the alteration is, the alteration mineralogy, what do you do? Let's say you're in the field for 3 or 4 weeks. You don't have a pocket XRD with you. What do you do in those when you're just not certain?
I mean, the best is just to identify everything that you see. I always map as an exploration geologist, and so I always have that lens. So whenever I'm mapping alteration, I try to make a heat map. Whatever I'm doing, I always try to figure out, is there somewhere that's heating up? And usually the most bulletproof ways to do that are to pattern out mineral abundance contours for example, chalcopyrite and pyrite. So you're going to find hopefully a domain where pyrite's higher, and maybe you start picking up chalcopyrite. And the other one that I've found that is always works really well is quartz vein abundance contours. And so I was actually pretty distressed when I got to Galore and realized that wasn't possible because it's a really easy way to show where things are heating up. And so you can start making domains and you say, well, I have 1 vein per 100 meters in this area of my map. And here I've got 5. And so now you've got almost a vector starting. So I think those are the best in terms of exploration anyway.
So case by case, if you don't have veins, you can't map their density. But following on from that, what if there's strong supergene oxidation? The sulfides are all gone. You're just left with gunk there. Of course, you have also the hypogene versus supergene mineralogy to distinguish. What happens if it really destroys the rock texture in terms of mapping the original lithologies?
Yeah, another really good question. One case I've done in the past where we had this, what we had was a pretty large alteration system, and all you really saw was that it was white. There was hardly anything to observe there. You could tell that there was some silicification, but we really didn't understand what was going on. So what I did was I mapped out the pits that were missing. And what I mean by that is, here you have your outcrop and you look at it with your hand lens, and, one outcrop will be 5% little pits, or, places where you can see little cubes. And I made a map with the abundance of those. And actually I was able to generate a pyrite halo out of that. So even though there weren't any sulfides to identify, I could still come up with abundance estimates. That doesn't really answer the hypogene versus supergene, but that can add a lot of complexity. Like, for example, in this case, there was some copper oxide and it was on very post-mineral intrusions. And so what the target was at the time was targeting those post-mineral intrusions, but it was just a secondary copper that was on it. And that copper was drawn out of this very large alteration system, which is what we ended up targeting. So it can definitely be tricky. I would try to focus on interpreting that primary sulfide presence, however you're able to do that. And in some cases, you can just look at the missing sulfide sites.
Okay, thanks. So basically still case by case, depending on what you have, you might have to be flexible, and textures are as important as the missing minerals.
Yeah.
Okay, thank you. So before another question, I just want to mention that I just put the link for anybody who wants to get the certificate out of this participation. So the next question is from Levi, I think. Would you like to unmute yourself and ask the question? Okay, if not, I can go for it. So the question is that, did the basement faults found in these deposits temporarily correlate to the timing of the conversion from the oceanic plate to North American plate around the Triassic time?
I would like to invoke Joanne again, if I can.
Sure.
Joanne, would you be able to talk about the Slide Mountain Ocean and maybe just paint that picture for them?
Sure. I would just ask for the last part of, they said something about the ocean continent transition in Triassic time. Is that correct?
Yes. Is there any temporal correlation between the convergence of the oceanic plate of North America with these faulting systems?
Oh, more than that, my dears. The Triassic is a really important time in the accretion of these offshore terrains to the ancestral North American continent. I've got a paper out with Bram Van Straten in Geosphere that will come out next year talking about this. Basically, Stikenia in the late Triassic collides with the neighboring terrain, Yukon-Tanana terrain, and in turn, Yukon-Tanana terrain goes ahead and collides with North America. So we're looking at a huge terrain wreck happening. And of course, the collision is going to reactivate a bunch of these basement faults within Stikenia. So like Gayle says, the faults were always there, but this generates a whole lot of stress at a certain time, and that's the framework for mineralization.
Okay, interesting.
Mm-hmm.
So the next question is almost the same one that I got, Aaron. So are the alteration assemblages widely different in the alkalic assemblages or overprints comparing to some systems that have the less potassic host rocks?
Okay, sorry, the question is, can you just try it one more time?
Yeah, it's about the alteration assemblages. So is there any difference comparing to the systems that are not that much alkalic? So what is exactly the alteration assemblages in the alkalic or overprint over here?
Okay, I guess I would just like to point out that every single porphyry system is unique, and the building the alteration model or interpretation should be done every time. So I would be careful not to generalize, but in general, I would say at Galore Creek, well, it's pretty interesting. You get some surprising assemblages. If you read up on some of the papers, you can learn more about this. But for example, a lot of garnet and things diopside, like in the core assemblages. But I mean, I think the most obvious difference is just there's no quartz. So at Mitchell we have 90% by volume quartz veins in a pretty significant area. And then at Galore Creek, no quartz. We get a little bit in the distal epithermal veins, just a little bit of quartz in the very latest veins. But I think what I also mentioned earlier is probably also the unique thing is that you can have K feldspar in the core, the proximal, and the distal alteration. And so, when I'm mapping, I'm always trying to come up with some kind of heat map or bullseye, right? So you want to figure out, where is the heart of that system and how do you drill it, basically. And what I see a lot of is people being quick to interpret a core assemblage once they see K feldspar. And that's a really common error. And it can be an expensive error as well if you're drilling. And I think being really careful not to just jump to putting those alteration assemblages in bags of, potassic. I mean, to me, terms like potassic, they're almost genetic. Like it's, when you say that, you've basically interpreted that you're in the heart of the system and that you have a drill target. I would be really careful. Always just build those assemblages and come up with a concept from there.
Thanks, Gayle. That question
Maybe getting off topic, sorry.
No, it was just kind of following up from what Jeff had asked about the alteration and how it looks when you're out in the field exploring these different porphyry systems out there. I was just wondering if, right, because you're right, like everything's potassic in an alkalic porphyry like this. Yeah,
it's quite incredible.
This isn't my question, but it was sent to me from Malango Mule. He asked about the influence of deformation after the porphyry mineralization, and was it like, did it help? I think he was unclear on your statement, and he's got a limited experience in shear zones. But how did the post mineralization deformation help concentrate? Did it help concentrate the ore basically, or did it play more of a dispersive role?
Yeah, that's what we think. And you can read a bit more about this in our papers, but the pressure solution cleavage, you're basically losing quartz along those pressure solution seams. And then what's left behind are, clays and sulfide. And so overall, the effect of that flattening is to homogenize the grade and potentially upgrade. But it is domain specific. So in the potassic zones, you won't see that effect. And then in the phyllic alteration, the high phyllosilicate alteration types, you'll have much more of an effect. And something that is pretty remarkable about Mitchell is that the grade is incredibly homogeneous. And It's really difficult to say how much of that is flattening, because some domains don't have flattening and they are also homogeneous. So, you know, maybe the phyllosilicate rich alteration types could have been more heterogeneous in grade and then made homogeneous. It's really not something we could prove or not. But certainly at the outcrop scale, you can demonstrate that, you know.
Yeah, no, that's really cool. I hope that answered Malango's question. And I will again mute myself. I'm talking too much for not hosting this. Thanks,
all right. No, thanks, Gayle, for the answers. We have one last question before we let you go. The last question is from Levi. Apologies if I'm saying that, pronouncing that incorrectly, but Levi wants to find out, do you think the structural network in these deposits that you just presented on are similar to the structural network in porphyries deposits along the Andes?
You know, I haven't had the chance to work in South America, so I would be nervous to speculate on that.
Answer. That was the last question for the evening. Before I let everyone go, I would just like to thank Gayle for the amazing talk. And also I would like to thank Joanne, who we just brought in without prior notice. So thanks for your contributions, really appreciated. To our participants, thanks again for attending our talks, and we will see you in 2 weeks' time for the final session of the 2021 season. With that said, that is goodbye from myself and the All Deposits Hub. Keep safe and keep warm, and good night or good afternoon or good morning.